This video covers the Taylor equation and the Taylor rule for the target Fed funds rate. There are at least three reasons to motivate the Taylor equation and rule. First, the Taylor equation helps predict how the Fed will react to inflation changes. Second, John Taylor, who created the Taylor equation and Taylor rule, argues that the Fed has made mistakes in the past, especially around inflation, and that setting the target Fed funds rate mechanically will help avoid those problems. And third, following the Taylor equation and rule may lead to a more stable economy. So let's look at the Taylor equation. But in order to do that, let's start with the Fischer equation. And the Fischer equation says the nominal interest rate equals a real rate plus the current inflation rate. Now, Taylor takes this Fischer equation and adds some gaps to the math. Let me show you. First, he adds an inflation gap, which is measured in percent. And that gap equals the current inflation rate minus the target inflation rate. And so what it says is that gap gets bigger as the current inflation rate goes higher relative to the Fed's target inflation rate. The other gap that he has in this equation is the output gap, and that's measured in percent also. And that's measured as the actual growth rate in GDP, gross domestic product, minus the growth rate of potential GDP. Now, potential GDP growth is an estimate of how much the economy can grow, assuming we are on a steady path with no business cycle swings. So what I like to show my students in class when I talk about this is you got an economy that's growing, it has business cycles, it has a business cycle, and all these swings have a cost to them in the sense that, look, we're going into high inflation, the economy's got to cool down a bit, it goes into recession, unemployment, and then here we go back to inflation and then unemployment. That's a hassle, that's a problem, and the point is, well, maybe what could happen is if we got rid of the business cycle through monetary policy, that the slope of that line, this straight line here, the slope, would actually increase. The slope of that line, and that line represents potential GDP, and the slope is the growth rate. And so if we can get rid of the business cycle and just have a straight line where the economy just keeps growing at a nice smooth rate, we probably could grow at a higher rate than what we have been. So that's the motivation here for looking at the output gap. So remember, the Fed has two mandates set by Congress: price stability, which means low inflation, and maximum employment, which basically means, look, you got to have a strong economy with strong GDP growth. And so the Taylor equation reflects those two mandates. So to be clear, when the inflation gap goes up, inflation is too high relative to the target, and the Fed will increase the Fed funds rate to reduce inflation in the future. That's the thought process for that positive 1/2 in front of the inflation gap. And the same thing works in the opposite direction. If inflation is less than the target, the Fed will reduce the Fed funds rate because the inflation gap will be negative. And so that will help spur the economy and actually increase inflation a little bit in the future to get that inflation gap close to zero. Now, applied to the output gap, when the economy is, quote, overheating too much, which means actual GDP is over potential, then that positive 1/2 is telling on that coefficient on the output gap, that's telling the Fed, increase the Fed funds rate to cool the economy down. And if the economy's growth rate in GDP is less than potential, that means the output gap is negative, and that implies that the Fed should reduce the Fed funds rate in order to spur economic growth. Now, let's apply this equation to the target Fed funds rate. And the way we're going to do that is we're going to take the Fischer equation, right? And so we're going to swap out that nominal rate, which is just a generic interest rate, and we're going to apply it to the target Fed funds rate. So that's the first thing. The second thing is we'll replace the real rate by what we call the natural real rate. The natural real interest rate is the interest rate that occurs when we have no business cycle. Like when we're on potential GDP, we're just on a straight line. The economy grows at a constant, say 3% growth rate with no swings, no unemployment, no high inflation, blah, blah, blah. It just grows nice and smoothly. What interest rate is consistent with that? That's called the natural rate of interest, the natural real rate. It's unobservable. You're not going to be able to spot it somewhere, but economists like to think that there is this natural real rate of interest. And then 3, to apply the Taylor equation, the third thing we want to do is we're going to place 1/2 in front of, in other words, 0.5 in front of the gaps as a way to scale the impact that they have on the target Fed funds rate. There's also another really tricky and subtle scaling effect that's going on in this equation. So as I just said, there's a 1/2 here in front of the inflation gap. That scales this because it reduces the effect of the inflation gap on the target Fed funds rate. But also right here, and you would never think of it, there's basically a 1.0 in front of there. But you don't have to multiply anything by 1 because it doesn't do anything mathematically. But keep in mind, there is a 1.0 in front of there. And why is that important? Well, because the total effect of inflation, these two terms, is the sum of those coefficients. So it's the 1.0 plus the 1/2 equals 1.5. So that means when inflation changes, current inflation changes, this number changes with a 1 coefficient in front of it. And this inflation gap, as I'll show you in a minute, has current inflation built into it. And so that has a scaling effect of 0.5. The total effect of a change in current inflation on this target Fed funds rate is 1.5. So it's 1.5 times the change in inflation that's going to matter here. And you're going to see that a little later on. That 1.5 is the heart of what's called the Taylor rule, which is buried in the Taylor equation. So when we get done, right here is the target Fed funds rate equation. So here we have target Fed funds rate. As I said, we swapped out the nominal rate. We now have a natural rate of interest, assuming there's no gaps, basically. So this rate assumes that there's no gaps. Get rid of this component, get rid of this component. And so then if there's no gaps, because there's no business cycle, then what we have is a target Fed funds rate equals the natural real rate plus an inflation rate, the current inflation rate. But as you know, we're not there. We're in the middle of a business cycle. The business cycle hasn't gone. It's going to be around for a while. And so these gaps do come into play. And it's a judgment call as to what these coefficients ought to be. They're 1/2, and that's what Taylor, when he created this rule, he used 1/2, and then he used 2% for the natural real rate. But you can adjust this equation. You know, the Taylor equation was created in the early 1990s. Things have changed. So the natural real rate may have changed, and then the coefficients can be adjusted as needed over time. So for our purposes, we're going to stick with this form of the equation. Just keep in mind that if you read other literature on the Taylor equation, you may see some slightly different coefficients. So let's apply this to an example. Let's suppose the natural real rate is 2%. As Taylor assumed, current inflation rate's 4, target inflation is 2, and that 2% target inflation rate is where the Fed is now. Let's say that GDP growth is only 1%, and potential GDP growth, assuming no business cycle, is 3%. The target Fed funds rate will be 6%. And so here's how it's calculated. 2% real, current inflation 4, current inflation again comes into the equation. This is target Fed funds. This is the target inflation rate. And then we have actual GDP and potential GDP growth rates. All boils down to 6%. Now let's assume the inflation rate increases from 3 to 7%. Let's see how this equation works, and this will lead us to the Taylor rule. So The target Fed funds rate, if we do this now at 7% inflation rate, the target Fed funds rate will be 10.5%. In other words, inflation rose by 3%, as I'm saying here, inflation rose by 3%, but the target rose by 4.5%. It went from 6 to 10.5%. And so the reason for that jump is that the sum of the coefficients on inflation are 1.5. The sum is 1.5. So that the 3% jump in inflation times the 1.5 gives us the increase in the Fed funds rate of 4.5%. That's the Taylor rule. The Taylor rule says that whatever the inflation rate increases, you multiply it by 1.5, and that's the increase in the Fed funds rate. And so you might ask, well, what do you mean? How does the Fed funds rate increase? With respect to the Fischer equation, well, there's an increase in the target Fed funds rate because there's an increase in the natural real rate of interest. Most economists believe that in order to slow the economy, the real interest rate has to increase. And so when you increase the Fed funds rate by more than the inflation rate, say by 1.5 times, then what you have is an increase in the natural rate. Let me show you here on the slide. From the previous equation, we determined that the target Fed funds rate was 10.5%. That was the result of an increase in inflation. Now what we're going to do is plug that into the Fischer equation. That's going to be the target Fed funds rate. And that's going to equal the natural real rate plus the 7% current inflation rate. Solving this equation for the natural real rate implies a natural real rate of 3.5%. Which is up from the 2% we just used for the natural real rate a few minutes ago. So again, it's the increase in the real interest rate that causes the economy to slow. So mathematically, to determine the effect on the natural real rate, it's a two-step process. First, use the Taylor equation to calculate the target Fed funds rate, then plug the estimated target Fed funds rate into the Fischer equation along with the current inflation rate and solve for a new natural real rate. So what you should realize from this discussion is when we talk about changing the Fed funds rate and the Fed changes the Fed funds rate up, say, to slow the economy or down to grow the economy, implicit in our discussion there is that, yeah, the Fed funds rate did go up, it did go down, but underneath it, the real rate has to change. The real rate has to be changing in order for the economy to grow or contract. To summarize what we just learned, let's go back to what I talked about at the beginning of the video. There's three motivations for studying the Taylor equation rule. First, the Taylor equation helps predict how the Fed will react to inflation changes. That was one thing. The second one was Taylor argued that the Fed has made a lot of mistakes in the past, and if it followed the Taylor equation and the Taylor rule, it would help avoid mistakes in the future. And three, the use of the Taylor equation may lead to a more stable economy. It's that last point that I want to elaborate on here with some history. In the 1970s, we had a couple of oil shocks that increased prices dramatically. We had inflation jumping up. And the Fed used to respond to that by increasing the Fed funds rate by the same amount of inflation. They figured, yeah, inflation jumped 3%, then we're just going to raise the Fed funds rate 3%. And when they did that, the real rate never changed. The natural real rate stayed the same. And when the natural real rate stayed the same, the economy didn't budge because of it. What they needed to do was raise the Fed funds rate higher than the increase of inflation, like the 1.5 times that I'm talking about here, in order to slow the economy down and reduce inflation. So that was a huge mistake made in the 1970s. Monetary policy did not slow the economy down to get rid of the inflation. Hence, we had really high inflation by the time we ended the 1970s and started to go into the 1980s. We had very high inflation. It's a good thing we have a firm grip on the Taylor rule now, so we can try to avoid that mistake in the future.